November 20th, 1942. The Western Desert, Egypt. The chalk squeaked against the blackboard as Sergeant George Pearson worked through calculations that would have baffled most university mathematics professors. Around him, a dozen British artillerymen of the 2nd Royal Horse Artillery watched in bemused silence as their sergeant filled the board with equations that seemed to belong in a Cambridge lecture hall rather than a desert gun pit. 300 yards away, across the scorched North African sand, German officers of Rommel's Afrika Korps trained their field glasses on the British position. Through the shimmering heat haze, they could see the absurd scene. A single British gunner, standing exposed beside a 25-pounder field gun, scribbling calculations like a schoolmaster. Hauptmann Klaus Richter lowered his binoculars and laughed. "The Tommies have gone mad from the heat. Look at him. One gun against an entire panzer regiment, and he's doing mathematics." His observation post overlooked what should have been a simple mopping-up operation. The main British forces had withdrawn during the night, leaving behind what German intelligence assumed was a skeleton rearguard, a few guns to slow the German advance while the bulk of the 8th Army escaped westward. Standard procedure, nothing to worry about. What Richter didn't know, what none of the German officers gathering to watch the curious British gunner could have imagined, was that they were witnessing the birth of an artillery technique so revolutionary it would be studied in military academies for the next 80 years. A method so precise it would allow a single gun to devastate targets that previously required entire batteries. A calculation so audacious that German veterans would speak of it in hushed tones decades after the war. The mathematics Sergeant Pearson was working through weren't just numbers. They were the future of artillery warfare. And in approximately 17 minutes, those equations would transform a quiet morning in the desert into a demonstration of British precision that would shatter German assumptions about their enemy's capabilities. The story of how one British sergeant with a gift for mathematics changed artillery warfare forever begins 6 months earlier in a dusty training ground outside Cairo. But to understand the magnitude of what happened that November morning, we need to understand what artillery could and couldn't do in 1942. Artillery in World War II was fundamentally a weapon of area bombardment. You didn't aim at a specific target. You aimed at a general location and hoped for the best. The standard doctrine taught in every artillery school from Fort Sill to Lark Hill was simple: fire lots of shells at a large area. Something will get hit. The mathematics behind this doctrine were equally simple. A typical British 25-pounder field gun, the workhorse of the Royal Artillery, could hit within 50 yards of its target under ideal conditions. That's a circle of error 100 yards across. In practice, with wind, weather, and worn barrels, that circle grew to 200 yards or more. To reliably destroy a point target like a tank or a building, doctrine called for a battery of 8 guns, firing multiple rounds each. The theory was that if you dropped enough shells in the general vicinity, probability would eventually put one on target. It worked, but it was wasteful. A battery might fire 200 rounds to destroy a single tank. This wastefulness mattered desperately in North Africa. Unlike the Western Front of the First World War, where ammunition arrived by the trainload, desert warfare was defined by supply constraints. Every artillery shell had to be trucked hundreds of miles from the coast. Water, food, and ammunition competed for the same limited transport capacity. British gunners in Egypt lived with constant ammunition rationing. A typical gun might have 50 rounds for an entire day's operations. Compare that to First World War bombardments, where guns fired thousands of shells in a single barrage. Desert gunners had to make every shot count. The Germans faced the same constraints, but they had an advantage. Their 88mm guns and their optical range-finding equipment were superior to British equivalents. A German gun crew could typically hit targets at longer ranges with fewer rounds. This technological edge had helped Rommel's Afrika Korps push the British back across Libya and into Egypt. By November 1942, Field Marshal Erwin Rommel's forces were in retreat after their defeat at El Alamein. But retreat didn't mean weakness. The Afrika Korps remained a formidable fighting force, skilled at ambush and counterattack. British commanders knew that every German position would exact a price in ammunition they could barely afford. Enter Sergeant George Pearson, a former civil engineer from Manchester who had joined the Royal Artillery in 1939. Pearson had a peculiar talent. He could visualize ballistic trajectories in his head. While other gunners relied on firing tables and basic trigonometry, Pearson understood the deeper mathematics of external ballistics. Before the war, he'd worked on bridge construction, calculating stress loads and structural dynamics. The mathematics of artillery weren't that different. A shell in flight was just another physics problem. Gravity, air resistance, wind drift, the Coriolis effect from Earth's rotation, all variables that could be calculated and compensated for. During training in England, Pearson's instructors had noticed something unusual. When other sergeant gunners achieved the expected accuracy of 50 yards, Pearson was consistently hitting within 20 yards. When asked how he did it, he showed them notebooks filled with corrections to the standard firing tables, adjustments for temperature, humidity, barrel wear, even the spin rate of the shell. His commanding officer, Major Robert Henderson, recognized something special. "Most gunners are craftsmen," Henderson later wrote. "They learn their trade through repetition and experience. Pearson was an artist. He understood the science behind the craft." In September 1942, Henderson gave Pearson an unusual assignment. "Work out how to make one gun do the work of 8. We can't afford to waste ammunition anymore." For 6 weeks, Pearson worked on the problem. He studied ballistics tables from the First World War. He corresponded with scientists at the Royal Artillery School. He conducted his own experiments, firing hundreds of practice rounds and meticulously recording every variable. Temperature, wind speed, humidity, even the time of day affected where shells landed. What Pearson discovered was that standard firing tables were approximations, good enough for area bombardment, but not precise enough for pinpoint accuracy. The tables assumed average conditions, but conditions in the desert were never average. Temperature could swing 40 degrees between dawn and noon. Wind patterns changed by the hour. Barrel wear from sand erosion affected each gun differently. Pearson developed what he called continuous correction methodology. Instead of using firing tables as gospel, he treated them as starting points. For each gun, he maintained a correction book that tracked that specific weapon's peculiarities. For each mission, he calculated fresh corrections based on current conditions. For each shot, he adjusted based on the results of the previous round. The mathematics involved were complex. Pearson had to account for dozens of variables simultaneously. But he developed shortcuts and mental calculation methods that let him work through the equations quickly. His notebooks, preserved in the Imperial War Museum, show page after page of elegant mathematical solutions to ballistic problems. By November, Pearson could achieve accuracy that seemed impossible. In one demonstration for skeptical officers, he put 5 rounds into a 10-yard circle at 3,000 yards range. This was precision that matched the best German guns, achieved with a standard British 25-pounder and nothing but mathematics. Major Henderson immediately saw the tactical implications. If we can hit reliably with a single gun, we can use our artillery completely differently. We don't need to mass batteries. We can spread guns out, make them harder to target, and still achieve devastating accuracy. But there was resistance. Artillery doctrine had barely changed since the First World War. The idea that one sergeant with a notebook could revolutionize gunnery seemed absurd to traditionalists. Some officers dismissed Pearson as a show-off. Others worried that his methods were too complex to teach to average gunners. Then came El Alamein. Montgomery's 8th Army smashed through Rommel's lines in a battle that consumed ammunition at staggering rates. British guns fired over 1 million shells in the opening bombardment alone. The victory was decisive, but it left British supply dumps dangerously depleted. As Rommel retreated westward, Montgomery pursued. But the pursuit would be ammunition limited. Standard doctrine said you needed artillery superiority to attack successfully. That meant massing guns and shells. But Montgomery didn't have enough shells to fight that way. This is where Pearson's methods suddenly became interesting to high command. If single guns could achieve battery-level accuracy, the Eighth Army could maintain pressure on Rommel's retreat with far less ammunition expenditure. Major Henderson proposed an experiment. Let Pearson's gun operate independently during the pursuit. See what one gun with perfect mathematics could achieve. On November 19th, Pearson's gun was detached from its parent battery and assigned to a motorized infantry column, pursuing the Afrika Korps across the western desert. His crew consisted of 6 men, Sergeant Pearson as gun commander and chief calculator, Bombardier James Cooper as his second in command. 4 gunners to load, aim, and fire. They were given 50 rounds of ammunition and orders to support the column's advance. If they encountered German resistance, they were to neutralize it with minimal ammunition expenditure. It was less an order than a challenge. Prove that one gun with superior mathematics could do what normally required a battery. The column moved out at dawn on November 20th. 2 companies of infantry and trucks, a platoon of armored cars for scouting, and Pearson's single gun towed behind a Morris truck. They drove west across empty desert, following the tracks of the retreating Germans. By mid-morning, the armored cars reported contact. German rearguard, estimated battalion strength, dug in around a small oasis settlement. The position blocked the only practical route forward. The infantry commander, Captain William Preston, assessed the situation and grimaced. Standard doctrine says we call for an artillery barrage, soften them up, then attack, Preston told Henderson over the radio. But we've got 1 gun and 50 shells. That's not enough for a proper bombardment. Major Henderson's response was simple. You have Sergeant Pearson. That's enough. Let him work. The German rearguard position was textbook Afrika Korps defense. They'd chosen ground that controlled the approaches, dug gun pits that provided protection and fields of fire, and positioned their anti-tank guns to cover the most likely attack routes. Approximately 300 men, well-armed and experienced. More importantly, they had artillery of their own. 2 88mm guns, the feared German dual-purpose weapons that could destroy tanks and blast infantry positions with equal effectiveness. These guns outranged Pearson's 25-pounder by 1,000 yards. If the British tried a direct approach, the German guns would tear them apart before Pearson could even return fire. Captain Preston studied the position through binoculars and didn't like what he saw. The Germans held the high ground around the oasis. Any British attack would have to cross 1,000 yards of open desert under fire. The armored cars didn't have the armor to survive that gauntlet. The infantry would be slaughtered. We need to wait for reinforcements, Preston said. Bring up more artillery, maybe some tanks. We can't assault that position with what we've got. Pearson had been studying the same position through a surveyor's telescope, but he was seeing something different. Where Preston saw an impregnable defensive position, Pearson saw a geometry problem. Angles, distances, heights, all calculable, all solvable. Sir, Pearson said carefully, I believe I can neutralize their artillery without exposing our forces to return fire. Preston turned to look at the sergeant. Their guns outrange us by a mile. How exactly do you plan to shoot at them without them shooting back? Indirect fire at extreme range, sir. I've worked out the mathematics. I can hit their gun positions from here. Here was 4,000 yards from the German position, a mile beyond the effective range of the German 88s. At this distance, the British force was completely safe. But it was also well beyond the normal effective range of the 25-pounder. The gun could theoretically fire that far, but hitting anything specific was considered impossible. Preston was skeptical. "Sergeant, I respect your confidence, but 4,000 yards is fantasy range. We'd be wasting ammunition." Pearson pulled out his correction notebook. "Sir, I've been calculating corrections since we left this morning. I know the current temperature, humidity, wind speed, and air pressure. I've measured the barrel wear on this specific gun. I've corrected for our altitude above sea level. I can put a shell within 20 yards of any point I choose." The claim was audacious, but Major Henderson had briefed Preston about Pearson's demonstrations back in Egypt, the impossible accuracy he'd achieved in controlled conditions. Preston made a decision. "All right, Sergeant. You have 5 rounds to prove your point. If you can't hit their artillery positions in 5 shots, we withdraw and wait for reinforcements." Pearson smiled. "I'll only need 3, sir." While his gun crew prepared the weapon, Pearson set up his blackboard. Yes, a blackboard. He'd liberated it from a destroyed school in Cairo and carried it in his truck specifically for this purpose. Complex ballistic calculations were easier to work through visually. The German officers watching through their field glasses found this hilarious. Here was a British sergeant, standing completely exposed at 4,000 yards, working mathematical equations on a blackboard like a university professor. The absurdity was too perfect. Hauptmann Richter called his fellow officers over. "Come watch the British professor. He thinks he can teach mathematics to artillery shells." Through German binoculars, they watched Pearson fill the blackboard with equations, parabolic trajectories, wind drift corrections, temperature compensations, the mathematics of external ballistics in their full complexity. Lieutenant Franz Weber, a former mathematics teacher before the war, actually recognized some of the equations. "He's calculating ballistic corrections, but those formulae are for laboratory conditions. You can't apply that level of precision in combat." "Of course not," Richter agreed. "This is theater. The British are trying to scare us with a show. 1 gun at maximum range, he'll be lucky to hit the desert, let alone our positions." The German officers were so confident that several of them remained standing in the open, watching the entertainment. Why take cover from a gun that couldn't possibly threaten them at this range? Pearson finished his calculations. He'd determined the exact elevation needed to send a shell on a 4,000-yard flight. He'd calculated the deflection needed to correct for the crosswind blowing from the north. He'd adjusted for the temperature, which was 17 degrees higher than the standard firing tables assumed. He'd even corrected for the spin drift, the slight curve a spinning shell makes in flight. Most remarkably, he'd calculated where to aim to hit a target he couldn't see. The German gun positions were behind berms of sand. From Pearson's position, they were invisible. But he knew where they had to be based on the defensive geometry. The Germans had positioned their guns to cover the approach routes, which meant they had to be in specific locations. Mathematics told him exactly where. "Elevation 47 degrees, Pearson called out. "Deflection left 2-3 minutes. Charge 4, high explosive." His crew worked smoothly. They'd practiced this countless times. The loader slammed a shell into the breech. The layer spun the elevation wheel to the precise angle. The traverse operator adjusted the deflection. Every movement was practiced, economical, professional. "Ready," Bombardier Cooper reported. Pearson checked the wind one more time. Still steady from the north at 12 miles per hour. The calculations held. "Fire." The 25-pounder roared. The recoil sent it rolling backward several feet. The shell arced into the sky, reaching an apex of nearly 3,000 feet, before beginning its descent. Flight time was 23 seconds. In the German positions, nobody was paying attention. Why would they? The British gun was miles away, firing at impossible range, probably a ranging shot that would land somewhere in the empty desert. The shell landed 6 feet from the nearest German 88. The explosion wasn't large. 25-pounders fired relatively small shells compared to heavier guns. But the blast was close enough to shower the German gun crew with sand and shell fragments. Close enough to make very clear that this was not a lucky shot. This was precise, deliberate targeting. The German officers watching through field glasses stood frozen in shock. The British sergeant couldn't have just done that. 4,000 yards was beyond the range where precision was possible. Yet the evidence was undeniable. The shell had landed exactly where it would do the most damage to the forward gun position. Hauptmann Richter grabbed his binoculars and focused on the British position. The sergeant was already working on his blackboard again, making adjustments, calculating corrections based on where that first round had landed. "Get everyone under cover," Richter shouted. "That was no accident. The British have some new ranging method." But he was wrong. This wasn't new ranging technology. It was mathematics. Pure, precise, beautiful mathematics. And Pearson's second shot was going to be even more accurate. Pearson studied the impact point through his surveyor's telescope, 6 feet short and 2 feet left. The shell had landed slightly closer than his calculations predicted. That meant the air was denser than standard tables assumed. The wind drift was marginally less than calculated. These were tiny errors, barely measurable. But Pearson could measure them and correct for them. He ran through his calculations again, adjusting for the new data. This time the math was easier because he had a reference point. The first shot had told him exactly how conditions were affecting shell flight. Now he could refine his aim. "Elevation 46 degrees, 5-8 minutes, Pearson called. "Deflection, left 2-1 minutes. Same charge, same shell type." His crew reloaded. The whole process took less than 90 seconds from firing the first shot to being ready for the second. German doctrine assumed that British guns at extreme range would need 5 to 10 minutes between shots to calculate new firing data. Pearson was proving that assumption wrong. The second shell flew true. This one landed 3 feet from the German 88, so close that the blast lifted the gun's trail off its pit and knocked the layer unconscious. The gun was undamaged, but temporarily out of action, its crew scrambling for cover. Watching from the command post, Richter felt cold fear settle in his stomach. This wasn't possible. The British didn't have precision artillery. Their doctrine was area bombardment, volume of fire, overwhelming their targets with quantity rather than quality. Yet here was a single gun, firing from impossible range, putting shells exactly where it wanted them. "Return fire," Richter ordered. "Have our guns engage that British position immediately." The second German 88, positioned 100 yards from the first, traversed to face the British. At 4,000 yards, this was at the absolute edge of its effective range, but the crew was experienced. They'd hit targets at long range before. The German gun fired. The shell was huge compared to the British 25-pounder. It screamed across the desert and exploded 200 yards short of Pearson's position. A good shot for the range, but not close enough to threaten the British. Pearson didn't even flinch. He was already working on his third calculation. The German gun had revealed its exact position when it fired. Now he knew precisely where both enemy guns were located. No more guessing based on tactical geometry. He had concrete target coordinates. The mathematics for the third shot were almost simple. He'd figured out all the environmental corrections from his first 2 shots. Now it was just a matter of applying those corrections to a new target point. 30 seconds of chalk on blackboard, and he had his solution. Elevation 47 degrees, 0-2 minutes. Deflection left 1-8 minutes. Fire when ready. The third shell landed in the gun pit of the second German 88. This time, the 25-pounder shell struck directly between the gun shield and the barrel. The explosion killed 2 crew members instantly and wounded 3 others. More critically, it damaged the gun's recoil mechanism. The weapon was out of action. In less than 5 minutes, using exactly 3 shells, Sergeant Pearson had neutralized both German artillery pieces. He'd done from 4,000 yards what normally required a battery, firing dozens of rounds at close range. And he'd done it with mathematics. The German infantry watching from their positions felt their confidence evaporate. The 88s were their shield against British tanks and their hammer for destroying enemy positions. Without those guns, they were vulnerable. Worse, they'd just watched a demonstration of British capability that rewrote their understanding of artillery warfare. If the British could hit specific targets at 4,000 yards, nowhere was safe. The carefully prepared defensive positions, the gun pits and fighting holes, all were now targeted with mathematical precision. The protection of distance had vanished. Lieutenant Weber, the former mathematics teacher, understood immediately what he'd witnessed. He's correcting for every variable in real time: temperature, wind, barrel wear, everything. That's not standard artillery practice, that's applied physics. Can our gunners do that? Richter asked. Not without extensive training in advanced mathematics, Weber admitted. What we just saw requires university-level understanding of ballistics, plus the ability to calculate rapidly under combat stress. I've never seen anything like it. In fact, nobody had seen anything like it, because Pearson's methodology was genuinely revolutionary. The German artillery had excellent guns and good optics, but their firing doctrine was still fundamentally the same as British doctrine: mass fire, area bombardment, probabilistic targeting. Pearson was demonstrating that precision was possible with existing weapons if you applied rigorous enough mathematics. Captain Preston, watching through his own binoculars, was equally stunned. He'd given Pearson 5 rounds to prove his concept. The sergeant had used 3 and achieved perfect results. The German artillery was neutralized without the British force suffering a single casualty. "Sergeant Pearson," Preston called, "can you do that again? Target their command post?" Pearson studied the German position through his telescope. The command post would be positioned somewhere behind the main defensive line, probably near the oasis, where there was some natural cover. He couldn't see it directly, but again, mathematics told him where it had to be. German infantry companies followed predictable organization patterns. The command post would be centrally located, approximately 300 yards behind the front line, positioned to have good visibility of the defensive position. There were only 2 spots in the German defensive layout that fit those criteria. "I can engage both possible locations, sir," Pearson said. 4 rounds total should suffice. Preston made a decision that would later be studied in staff colleges as an example of adaptive tactics. Instead of calling for infantry assault, he would let Pearson systematically dismantle the German position with precision fire. 1 gun, minimal ammunition expenditure, maximum effect. "You have carte blanche, Sergeant. Take that position apart piece by piece." What followed was a masterclass in precision artillery. Pearson walked his fire through the German position with methodical precision. Each shot was calculated, fired, observed, and corrected. Each impact landed within yards of its intended target. Shot 4 hit the suspected command post location. A near miss, but close enough to force the German officers to relocate. Shot 5 destroyed a machine gun position that had been carefully camouflaged. Pearson had identified it by the slight discoloration in the sand where the crew had built overhead cover. Shot 6 landed among a mortar section, killing the section leader and destroying 2 of their 3 weapons. Shot 7 found the relocated command post. This one was direct hit. Hauptmann Richter survived because he'd stepped outside the dugout moments before impact, but his radio operator and 2 other officers died instantly. By shot 8, the German position was in chaos. Soldiers were abandoning their fighting positions and falling back toward the oasis. The careful defensive line was dissolving as troops decided that staying in position meant being targeted by the impossibly accurate British gun. Pearson continued firing. Shot 9, shot 10. Each one precisely placed, each one destroying a specific target. Gun pits, supply dumps, vehicle positions. He was conducting a 1-gun barrage with the precision of a surgeon. The psychological impact on the Germans was devastating. Artillery was supposed to be an area weapon. You took cover, and hoped the random chance of shell fall spared you. But this wasn't random. This was targeted. The British gunner could apparently see through sand and camouflage, could identify specific positions, and could hit them reliably at impossible range. After shot 12, the German rearguard broke. Officers ordered a withdrawal to secondary positions 2 miles west. They abandoned equipment, destroyed what they couldn't carry, and retreated in considerable disorder. The position they'd held confidently that morning was abandoned by afternoon. Pearson had used 12 shells. A standard artillery barrage against this position would have required at least 200 rounds from multiple guns. He'd achieved the same effect with 6% of the normal ammunition expenditure. Captain Preston led his infantry forward to occupy the abandoned German position. They found the evidence of Pearson's accuracy everywhere. Shell craters within feet of gun positions, destroyed equipment, shattered vehicles. Every impact had hit something valuable. More telling were the German dead. In a normal artillery barrage, most casualties resulted from random shell hits. Here, nearly every fatality was a gun crew member or an officer. Pearson had systematically targeted the Germans' most valuable personnel, the specialists who operated weapons, and the leaders who coordinated defense. "It's like he could see through the sand," one British corporal said, examining a gun pit that had taken a direct hit. How did he know this was here? The answer was mathematics and tactical understanding combined. Pearson understood how German units organized their defenses. He knew where key positions had to be located based on the terrain and tactical requirements. Then he used mathematics to hit those calculated positions with precision that seemed supernatural. That evening, Major Henderson arrived to inspect the battlefield personally. He walked through the abandoned German positions with Pearson, examining each impact crater. 12 shots, Henderson said quietly. 12 hits, at 4,000 yards. Do you understand what you've accomplished here? Pearson shrugged uncomfortably. He didn't like attention. Just mathematics, sir, applied properly. No, Henderson corrected. This is a new form of warfare. You've proven that precision artillery isn't just possible, it's practical. One gun with proper mathematics can do what previously required batteries. Henderson immediately filed a report to higher headquarters describing the engagement. The report made its way up the chain of command, eventually reaching Montgomery's desk. The 8th Army commander recognized the implications immediately. If British artillery could achieve this level of precision, it changed the mathematics of desert warfare. The 8th Army could maintain pressure on Rommel's retreat with fewer guns and less ammunition. They could conduct operations that previously would have been impossible due to supply constraints. Montgomery ordered Pearson back to Cairo to demonstrate his methods to artillery instructors. Over the next 2 weeks, Pearson conducted a crash course in precision gunnery for selected sergeant gunners. Not all of them had the mathematical aptitude to master his full methodology, but the basic principles could be taught. The key insights were simple enough. Maintain detailed records of each gun's individual characteristics. Calculate fresh corrections for each mission based on current conditions. Observe and adjust based on actual results, rather than theoretical tables. These principles didn't require genius-level mathematics. They just required discipline and attention to detail. By December 1942, a dozen British guns in North Africa were applying Pearson's methods. By January, it was 100 guns. The improvement in accuracy was immediate and dramatic. British artillery effectiveness increased, while ammunition consumption decreased. The Germans noticed. Intelligence reports began describing British artillery as unnaturally accurate. German soldiers reported being targeted by precision fire that seemed impossible at the ranges involved. Some reports bordered on the supernatural, claiming the British had developed psychic gunners who could see through solid earth. The truth was more mundane, but more significant. The British had simply applied rigorous mathematics to a weapon that had previously been used imprecisely. They'd taken a tool designed for area bombardment and turned it into a precision instrument through nothing but calculation and discipline. German artillery officers studied, captured British firing data, and were baffled. The correction factors Pearson used went far beyond anything in German doctrine. His methods compensated for variables that German gunners didn't even measure: temperature gradients in the propellant, microscopic variations in shell weight, the effect of barrel heating on interior ballistics. One captured German artillery officer, shown Pearson's correction notebooks during interrogation, reportedly said, "This is not military doctrine. This is doctoral-level physics applied to gunnery. No wonder your accuracy improved. You're not fighting the same war we are." He was right. Pearson had fundamentally changed artillery warfare, not through new technology or different weapons, but through better mathematics. He'd proven that intellectual advantage could be as decisive as material advantage. The story of Sergeant Pearson's precision gunnery spread through the British Eighth Army like wildfire. Artillerymen who had struggled with the frustration of inaccurate fire suddenly had a methodology that worked. Gunners who had wasted dozens of rounds destroying single targets could now do it with a handful of shells. More importantly, Pearson's methods restored artillery's reputation. In the early desert campaigns, British artillery had been outranged by German guns and forced to operate at a disadvantage. Now, British guns could hit reliably at ranges where German guns struggled. The technological disadvantage was overcome through mathematical superiority. The Battle of Mareth Line in March 1943 showcased the new capabilities. British artillery, using Pearson's precision methods, supported the attack with an accuracy that surprised both friend and foe. Specific German strong points were targeted and destroyed with minimal ammunition expenditure. Counter-battery fire knocked out German guns with first-shot hits that seemed miraculous. Lieutenant Franz Weber, the German mathematics teacher turned artillery officer, was captured at Mareth. During his interrogation, he specifically asked about British gunnery methods. When shown Pearson's correction notebooks, he studied them carefully. "This explains everything," Weber said. "We thought you had new guns, or new shells. But you just used old guns better than we use ours. How many of your gunners can calculate like this?" The interrogating officer admitted that only a small percentage of British gunners had the mathematical training to apply Pearson's full methodology. But even those who couldn't master the complex calculations could use simplified versions that significantly improved accuracy. Weber nodded slowly. "You've industrialized precision. That's very British, very practical. We Germans prefer technological solutions. Better guns, better optics, better shells. But you've proven that sometimes the solution is just better mathematics." By mid-1943, Pearson's methods were being taught at the Royal Artillery School at Larkhill, not as a replacement for conventional gunnery, but as an advanced technique for situations requiring precision. The curriculum included intensive mathematics training, environmental measurement protocols, and rapid calculation methods. The program produced a new kind of artilleryman. These gunners combined the traditional skills of their trade with scientific understanding of ballistics. They maintained meteorological logs. They measured barrel erosion with precision tools. They calculated corrections that previous generations would have considered impossibly complex. The effect on British artillery effectiveness was measurable. Ammunition expenditure per target destroyed dropped by 30 to 40%. First-round hit probability tripled. Mission success rates increased dramatically. And all of it was achieved with existing weapons through nothing but better application of physics. The Americans, when they learned of Pearson's methods, were fascinated. U.S. Army artillery observers watched demonstrations at Larkhill and immediately recognized the value. American artillery doctrine was even more focused on mass fire than British doctrine. The idea that precision could reduce ammunition needs was compelling. By late 1943, American artillery schools were incorporating elements of Pearson's methodology into their training. The Americans added their own innovations, particularly around meteorological measurement and systematic data recording. The collaboration between British mathematics-focused approach and American industrial systematization produced artillery methods that were devastatingly effective. In Normandy, in June 1944, Allied artillery dominance was partly built on the foundation Pearson had laid. British and American guns could hit targets with precision that the Germans couldn't match. Counter-battery fire was swift and accurate. Infantry support was reliable and deadly. The Allied artillery arm had evolved from a blunt instrument into a precision weapon. German artillery officers captured after D-Day consistently reported being shocked by Allied gunnery accuracy. They described British and American fire as surgical and uncannily precise. Some reports claimed Allied gunners must have forward observers with direct line of sight to targets. The reality was that they were just calculating properly. By the war's end, Pearson's revolutionary methods had become standard doctrine throughout the Royal Artillery. What had seemed impossible in November 1942, precision fire at extreme range, was now routine. Young gunners learned correction mathematics as part of basic training. Every gun crew maintained correction logs. Precision was no longer exceptional. It was expected. The personal story of Sergeant George Pearson had a quieter ending than his revolutionary methods deserved. He continued serving as an artillery instructor through 1944, teaching his methods to successive classes of gunners. He never sought publicity or recognition for his innovations. Mathematics and gunnery were just problems to be solved, in his view. In January 1945, Pearson was promoted to warrant officer and assigned to a staff position at the School of Artillery. He spent his remaining service writing training manuals and refining calculation methodologies. His Handbook of Precision Gunnery became required reading for British artillery officers. After the war, Pearson returned to civil engineering. He worked on bridge reconstruction in Europe, applying the same rigorous mathematical approach to structural engineering that he'd brought to artillery. He rarely spoke about his war service. When asked about the precision gunnery methods that bore his name, he'd shrug and say they were just common sense applied properly. He died in 1973, largely unknown outside artillery circles. His obituary in the Manchester Guardian mentioned his engineering career, but barely touched on his military service. The revolutionary methods he'd developed were by then so thoroughly integrated into artillery doctrine that their origin was forgotten by most. But in artillery schools from Larkhill to Fort Sill to Petawawa, Pearson's methods continued to be taught. The mathematics of precision fire, the environmental correction factors, the systematic data recording, all of it traced back to a sergeant with a blackboard in the North African desert. What made Pearson's achievement remarkable wasn't the mathematics themselves. The physics of ballistic trajectories were well understood by 1942. University professors could calculate shell flight paths to absurd precision in laboratory conditions. What Pearson did was apply that academic understanding to combat conditions. The challenge was speed. In a laboratory, you could spend hours calculating the perfect firing solution. In combat, you had minutes at best. Pearson developed mental shortcuts and simplified calculation methods that gave precise answers quickly enough to be tactically useful. His correction methodology worked like this. First, establish a baseline using standard firing tables. These tables, developed through decades of testing, provided starting point estimates for range, elevation, and expected accuracy. Second, measure current conditions: temperature, humidity, wind speed, air pressure, even time of day all affected shell flight. Third, calculate corrections for each variable. This was where Pearson's mathematical talent showed. He could rapidly compute how much each environmental factor would affect the shell's trajectory. Fourth, apply gun-specific corrections. Each artillery piece had individual quirks. One gun might shoot slightly left due to bore wear. Another might have a weak breech spring affecting velocity. Pearson maintained detailed records of these characteristics for every gun he worked with. Fifth, fire and observe. The first round was a test shot that revealed how accurate your calculations were. Sixth, correct and fire again. Based on where the first shell landed, you could refine your calculations and adjust your aim. The entire process sounds slow when written out. In practice, Pearson could run through all 6 steps in under 2 minutes. His blackboard wasn't just for show. The visual representation of the mathematics helped him work through complex calculations faster than purely mental arithmetic would allow. The specific equations Pearson used were variations of the ballistic coefficient formula that related drag force to projectile characteristics. He calculated wind drift using a simplified form of the Poncelet equation. His temperature corrections were based on the relationship between air density and drag. All of these were known physics. Pearson's innovation was making them usable under combat stress. What's fascinating from a modern perspective is how close Pearson came to modern artillery doctrine with nothing but 1940s technology. Today's self-propelled guns have ballistic computers that automatically calculate the corrections Pearson worked out on his blackboard. They have weather stations that precisely measure environmental conditions. They have laser rangefinders that eliminate distance uncertainty. But the underlying mathematics are still Pearson's mathematics. The correction factors modern computers apply are refined versions of the factors he calculated by hand. The systematic data recording that modern fire direction centers use traces directly to the methods Pearson developed in the desert. Military historians studying artillery evolution consistently identify Pearson's work as a pivotal moment. Before Pearson, artillery was fundamentally imprecise. After Pearson, precision became achievable. The weapon didn't change. The shell didn't change. The gun didn't change. Only the mathematics changed, and that changed everything. The German response to British precision gunnery is equally instructive. German artillery officers recognized what the British had achieved and tried to replicate it. But German military culture struggled with the concept. German doctrine emphasized technological superiority and tactical brilliance. The idea that superior mathematics could overcome technological disadvantage was foreign to their thinking. Some German artillery units did develop their own precision methods, but these were never standardized across the force. German artillery remained primarily a weapon of mass fire throughout the war. They continued to rely on volume rather than accuracy, quantity rather than quality. This represented a broader pattern in the German war effort. The Germans pursued technological solutions to military problems, while the Allies often pursued methodological solutions. German tanks were more sophisticated than Allied tanks, but Allied tanks were produced in overwhelming numbers. German aircraft were technologically advanced, but Allied aircraft were flown by better-trained pilots with superior logistics support. Pearson's precision gunnery fit this pattern perfectly. The British didn't develop better guns to counter German artillery superiority. They developed better mathematics to use their existing guns more effectively. The solution was intellectual rather than technological, and it worked brilliantly. The broader lesson extends beyond artillery. Pearson proved that systematic application of scientific principles could dramatically improve military effectiveness without requiring new equipment. This was a very economical form of military innovation. Teaching better mathematics costs far less than manufacturing new weapons. In modern military terms, Pearson demonstrated force multiplication through intellectual advantage. One gun with superior fire direction could achieve the effect of multiple guns using conventional methods. The multiplication factor was significant, approaching 5-to-1 in some circumstances. That meant the British effectively increased their artillery strength by a factor of 5 without building a single new gun. From a strategic perspective, this kind of innovation was exactly what Britain needed in 1942. The British Empire was resource-constrained, fighting on multiple fronts, struggling to match German industrial output. Innovations that achieved more with less were worth their weight in gold. Pearson's methods did exactly that. Behind the mathematics and the tactical innovations was a very human story. George Pearson was not a career soldier seeking glory. He was a civilian who joined the military out of duty and applied his peacetime skills to wartime problems. His genius was recognizing that the tools he'd used for bridge engineering could be adapted to artillery. The 6 men in his gun crew were equally ordinary. Bombardier James Cooper had been a bank clerk. The gunners were a farmer, a factory worker, a shop assistant, and a school teacher. None of them had advanced mathematics training, but they learned to follow Pearson's methods through drill and repetition. Cooper later described the experience in a letter preserved in the Imperial War Museum archives. "We didn't understand half the mathematics the sergeant was doing, but we learned to trust it. When he said elevation 47 degrees, we said elevation 47 degrees. When he said fire, we fired, and the shells landed where he said they would. After the first few times, it stopped seeming like magic and started seeming normal." This trust was essential. Precision gunnery required the entire crew to execute their tasks perfectly. A small error in setting the elevation or the deflection would throw off Pearson's calculations. The crew had to be as precise in their actions as Pearson was in his mathematics. The German officers who witnessed Pearson's demonstration had a different perspective. For them, the experience was devastating. They'd spent years developing expertise in desert warfare. They understood the capabilities and limitations of artillery. Then a single British sergeant with a blackboard rewrote all the rules. Hauptmann Klaus Richter survived the war and was interviewed in 1968 for a British documentary about North African campaigns. He spoke about the November 20th encounter with remarkable clarity. "We were absolutely confident that morning," Richter recalled. "We held good positions. We had superior guns. The British had one gun at impossible range. We actually laughed at them. Then the first shell landed, and we stopped laughing. By the third shell, we were terrified. By the 10th shell, we knew we had to retreat. One British sergeant had defeated an entire battalion, not through firepower, but through precision." Richter admitted that the psychological impact was worse than the physical damage. Losing 2 guns, and perhaps 20 men, was tactically insignificant. But losing our confidence in our defensive positions was devastating. After that day, every time we dug in, we wondered if there was a British gunner calculating how to hit us from beyond visual range. The fear of invisible precision was paralyzing. This psychological dimension of Pearson's achievement is often overlooked. The physical effect of his precision fire was significant, but limited. He destroyed guns and killed soldiers, yes, but not in numbers that dramatically affected the strategic situation. The psychological effect was far larger. German troops who faced precision, British artillery became cautious, defensive, reluctant to hold fixed positions. This caution slowed their operations and degraded their effectiveness. Lieutenant Franz Weber, the captured German artillery officer who studied Pearson's notebooks, became something of an advocate for mathematical gunnery among his fellow prisoners of war. He gave lectures explaining the British methods and arguing that German artillery needed to adopt similar approaches. "We were outthought," Weber told his fellow prisoners. "Not outfought, not overwhelmed by superior numbers, but outthought. A British sergeant with a blackboard defeated our 88s with mathematics. That should humiliate us, but instead it should teach us. Intelligence and method can overcome material advantage." Weber's lectures were recorded by British intelligence and preserved in the National Archives. They provide fascinating insight into how German military professionals processed their defeat. Many refused to accept that mathematical superiority could trump technological advantage. Others, like Weber, recognized that the British had found a genuine innovation that changed warfare. After the war, several German artillery officers visited Britain specifically to meet Pearson and learn his methods firsthand. These visits were remarkably cordial. Former enemies discussed ballistics and calculation methodologies with the passion of academics debating theory. The mathematics transcended national rivalry. One of these visitors was Colonel Heinrich Müller, who had commanded German artillery in North Africa. He and Pearson spent an afternoon in 1952 going through firing calculations on a blackboard in Pearson's Manchester office. Müller later wrote that it was one of the most educational experiences of his military career. "I finally understood what happened to us in the desert," Müller wrote. "We were fighting with 19th century methods against 20th century mathematics. Pearson showed me that every variable we ignored, temperature gradients, barrel wear, even the rotation of the Earth, could be measured and compensated for. The precision he achieved wasn't magic. It was just extremely rigorous application of physics." The friendship between Pearson and several former German artillery officers speaks to something important about military innovation. The best innovations aren't jealously guarded secrets. They're ideas that spread because they're genuinely useful. Pearson never tried to keep his methods secret. He published them, taught them, and discussed them openly with anyone interested. This openness accelerated the spread of precision gunnery methods. By the 1950s, artillery forces worldwide were adopting mathematical approaches to fire direction. The French, the Americans, the Canadians, even the Soviets developed their own versions of Pearson's methodology. Artillery warfare evolved globally because one sergeant had shared his mathematical insights freely. The 25-pounder gun that Pearson used in his November demonstration was preserved after the war. It sits today in the Royal Artillery Museum at Woolwich. A small plaque describes its service record, but nothing about the revolutionary methods developed around it. The gun itself is unremarkable. Thousands like it were built during the war. What made this particular gun special was the mind that aimed it. The calculations that turned a standard field gun into a precision instrument. The methodology that transformed artillery warfare. These intangibles don't preserve well in museums. They live on in doctrine and training. Modern artillery bears Pearson's fingerprints throughout. The fire direction centers that calculate firing solutions use computerized versions of his correction methodologies. The meteorological stations that measure atmospheric conditions are descendants of Pearson's environmental measurement protocols. The systematic data recording that tracks every gun's individual characteristics traces directly to Pearson's correction notebooks. Even the basic concept that artillery can and should achieve first-round hits through rigorous calculation is Pearson's legacy. Before him, artillery accepted that precision required multiple ranging shots. After him, precision on the first round became the standard to aspire to. Modern artillery achieves this through technology, but the underlying philosophy is Pearson's. The evolution of artillery since World War II has been toward ever greater precision. Laser-guided shells, GPS-directed projectiles, drone-spotted targets. All of these represent technological paths to the same goal Pearson achieved with mathematics alone, putting shells exactly where you want them. There's a direct intellectual lineage from Pearson's blackboard calculations to modern precision strike weapons. The Excalibur GPS-guided artillery round, which can hit within 10 meters of its target from 30 kilometers away, is the technological fulfillment of Pearson's vision. Artillery as a surgical instrument, rather than a blunt weapon. Military academies studying artillery evolution identify three pivotal innovations that created modern gunnery. The development of indirect fire in the late 19th century, Pearson's precision methodology in 1942, and the introduction of guided munitions in the 1980s. Pearson sits in the middle of that triad, linking traditional and modern artillery. What's remarkable is that Pearson's innovation required no new technology. The 25-pounder gun was designed in the 1930s. The mathematics he used were 19th century physics. The meteorological instruments he employed were standard commercial equipment. Everything he needed already existed. He just combined existing tools in a new way. This kind of innovation, recombining existing capabilities to achieve new effects, is often more valuable than purely technological innovation. It's faster to implement, cheaper to scale, and more accessible to forces with limited industrial capacity. Pearson proved that intellectual advantage could be achieved immediately without waiting for new weapons. The British military's response to Pearson's innovation was remarkably swift by institutional standards. Within 6 months, his methods were being taught systematically. Within a year, they were standard doctrine. This rapid adoption happened because the innovation was demonstrably superior and required no new equipment. Commanders could implement it immediately just by training their gunners differently. Compare this to technological innovations, which often took years to move from prototype to battlefield deployment. A new gun design needed to be tested, manufactured, and distributed. A new ammunition type required factory retooling, but Pearson's methods just required better training. Any artillery unit could adopt them tomorrow if their gunners learned the mathematics. This accessibility meant Pearson's innovation spread beyond the British military, faster than most technical advances. Allied forces adopted it quickly. Even former enemy forces adopted it after the war. By the 1950s, precision gunnery based on mathematical correction was essentially universal among professional military forces. The story of November 20th, 1942, remains instructive for modern military professionals. It demonstrates that innovation doesn't always mean new technology. Sometimes it means using existing technology better. Pearson didn't invent anything. He just applied known physics more rigorously than anyone had before. This has implications beyond artillery. Many military capabilities could potentially be improved through better methodology rather than new equipment. Better training, better doctrine, better application of scientific principles. These intellectual advantages can be as decisive as material advantages. The German officers who mocked Pearson's blackboard calculations learned this lesson painfully. They assumed artillery was fundamentally a weapon of approximation. They accepted inaccuracy as inherent to the technology. Pearson proved them wrong. Artillery could be precise. It just required doing the mathematics properly. That lesson, that assumed limitations can sometimes be overcome through intellectual rather than technological means, resonates beyond World War II. Modern military forces still struggle with the balance between pursuing new technology and better employing existing capabilities. Pearson's example suggests that both approaches have value, but methodological innovation is often faster and cheaper. On November 20th, 1942, German officers watched a British sergeant work mathematics on a blackboard and laughed. The idea that calculations could overcome their defensive advantages seemed absurd. Artillery was an approximate weapon. Precision at extreme range was impossible. Everyone knew this. Sergeant George Pearson didn't know this was impossible. Or rather, he knew the mathematics said it was possible if you calculated properly. So he calculated properly. He measured every variable. He corrected for every environmental factor. He applied physics rigorously. And he put shells exactly where he intended them from 4,000 yards away. 12 rounds, 12 hits. A German battalion forced to retreat by one gun and one sergeant's mathematics. The demonstration was small in scale, but enormous in implication. If precision was possible, artillery doctrine had to change. If one gun with proper calculations could do what previously required batteries, force structure had to change. If mathematical advantage could overcome technological disadvantage, Training had to change. All of these changes happened. Pearson's demonstration that morning in the Western Desert sparked a revolution in artillery warfare that continued for decades. The methods he developed became doctrine. The precision he achieved became expectation. The mathematical rigor he applied became standard. The German officers who mocked Pearson learned respect for British artillery the hard way. They discovered that assumptions about weapon capabilities could be wrong. They found that intellectual innovation could be as decisive as technological superiority. Most importantly, they learned that underestimating your enemy based on preconceptions was a fatal mistake. Hauptmann Klaus Richter, who had called Pearson's calculations theater and mockery, spent the rest of the war respecting British gunnery. He survived to 1968 and gave interviews about his experiences. He always mentioned November 20th, 1942, as the day he stopped underestimating the British. "We thought we understood artillery," Richter said in his final interview. "We had good guns, good training, good doctrine. Then a sergeant with a blackboard showed us we understood nothing. Real mastery isn't about having the best equipment. It's about using your equipment to its absolute maximum potential. The British did that. We didn't. That's why they won." Lieutenant Franz Weber, the captured mathematics teacher, returned to teaching after the war. He incorporated Pearson's ballistic calculations into his physics curriculum. His students in Bremen learned about trajectory mathematics through the story of a British sergeant who outcalculated German artillery in the desert. Weber considered it an important lesson about the practical application of theoretical knowledge. Pearson proved that physics matters, Weber told his students, not just in laboratories, but in the real world. The same mathematics that describe falling apples describe falling shells. Understanding those mathematics precisely gave him a decisive advantage. Never forget that knowledge, properly applied, is power. Sergeant George Pearson himself never claimed to have revolutionized anything. When interviewed for artillery publications after the war, he downplayed his innovations. "I just did the mathematics properly," he insisted. "Anyone with decent training in physics and ballistics could have done the same. I'm surprised nobody thought of it earlier." But someone had to think of it first. Someone had to recognize that artillery could be more precise if you calculated more carefully. Someone had to develop the methodologies, work out the shortcuts, prove the concept under combat conditions. Pearson was that someone. His modesty about his achievements doesn't diminish them. The blackboard he used that morning in November 1942 wasn't preserved. It was just a piece of wood with chalk residue, abandoned when the British column moved on. But the calculations written on it changed warfare. They proved that precision was possible. They demonstrated that mathematics mattered. They showed that one brilliant mind could make a strategic difference. Today, artillery officers around the world learn Pearson's principles even if they don't know his name. They maintain firing logs that track gun-specific corrections. They measure meteorological conditions carefully. They calculate precise firing solutions before engaging targets. They expect first-round hits. All of this traces back to a sergeant in the desert who refused to accept that artillery had to be imprecise. The impossible shot that destroyed German confidence that November morning wasn't really impossible. It just seemed impossible to those who hadn't done the mathematics properly. Pearson did the mathematics. The shells landed where physics said they would, and artillery warfare changed forever. German officers mocked the British artilleryman until his calculations blew apart their position. Then they stopped mocking. They started learning. And they carried the lesson of November 20th, 1942 for the rest of their lives. Never underestimate an enemy with better mathematics. That lesson remains relevant. In an age of precision-guided munitions and computer-calculated firing solutions, it's easy to forget that precision began with a man, a blackboard, and a willingness to do the calculations that others assumed were impossible. George Pearson proved that sometimes the most revolutionary weapon isn't a new gun, it's a better equation. The thunder of the 25-pounder that morning echoed across more than just the Western Desert. It echoed through artillery doctrine for generations. Every precision strike since owes a debt to the sergeant who proved it could be done. Every first-round hit validates his mathematics. Every artillery officer who refuses to accept close enough carries forward his legacy. On November 20th, 1942, mathematics defeated mockery. Precision defeated assumption. Knowledge defeated arrogance. And one British sergeant with a blackboard changed warfare forever. The Germans laughed at his calculations. Then his calculations destroyed their guns, scattered their forces, and rewrote the rules of artillery combat. That's the power of doing the mathematics properly. That's the legacy of Sergeant George Pearson. That's the story of the impossible shot that proved precision was possible all along.